Oh, thank you, Linda, and also thank you, Christina, for having us on this ISPE event. So yes, I'm going to talk about a technology which has been around for many years, but not so much for within the pharma industry. So what I want to present is some background on solvents, the use of solvents in pharmaceutical industry. Then I will continue to explain the MPPE technology as we know it and how we can use it in that industry, and that will be illustrated by a case study on toluene removal. Feel free to ask some questions during the presentation. I also have some questions from my side for the audience, so those will be shown as well as a poll. So the pharmaceutical market solvent usage. Basically, we can distinguish three main steps when producing a medicines or pharmaceutical products. And this starts obviously with R&D to develop a new type of medicine, and that eventually needs to be produced on a larger scale for applying it by consumers. And that manufacturing, the most important step is that manufacturing of the API, so the active ingredient. And for that, there are different routes to do that. There is a chemical synthesis, biological synthesis, and yeah, the latter can have different processes like extraction, fermentation, and bioprocessing. Once the API has been manufactured, obviously it needs to be put in some type of form, a tablet or a serum, and that is yeah, basically the step of finished product manufacturing. Well, the use of solvents, which is a target for our technology, is mostly done during the API manufacturing. And it is a significant amount of solvents is being consumed. If you look at the number of API sites around the world, and there are more than 1,300 globally, which means there are a lot of sites that use solvents and eventually have to do something with those solvents after they leave the process. So the first poll, I'm obviously not aware of the exact composition of the audience, but I guess you have been dealing with API manufacturing and therefore also with solvents. So I was wondering what type of solvents you most commonly see in your API manufacturing sites. So I've listed the most common ones: acetone, dichloromethane, DMSC, ethanol, methanol, toluene, but there are others as well. So feel free to reply to this question. And obviously within an API site, you have use of multiple solvents, but I'm just curious to get your feedback on which ones are most commonly used in, let's say, the highest volumes. Okay, so we see acetone as basically together with methanol, the most common ones. It seems to be relatively evenly distributed. Only DMAC, which has been used in several processes, is not recognized by most of your people. Okay, that I will continue to the next slide, and there you will see some. Wait a minute. You will see some feedback coming from a study from the US. And also in this case, you see methanol being used a lot, as well as dichloromethane. What is not listed here is acetone and ethanol, because these are, let's say, the solvents in this graph that actually are regarded as toxic when released to the environment. And both acetone and ethanol are not categorized as that. But you see the majority is indeed the well-known substances, as you pointed out as well. But there are also quite a number of more exotic solvents like NMP, DMF, etc. So the reason that I'm highlighting this is that although few solvents are used as a majority, there are significant more other types to be used in the pharmaceutical industry as well. And that poses some problems in the treatment of those solvents. If we look at the final destination of the solvents in the pharmaceutical industry, then we can distinguish two types of streams containing these solvents. We have the highly concentrated streams, that's coming from, for instance, from the extraction of a mother liquid. And the solutions for that are typically that they are treated on site by distillation. Although this is a common practice, I would say it does have some risk on cross-contamination that needs to be managed. So if a large API site has these kind of facilities, there's also a lot of administration attached to it to make sure and quality control to make sure that whatever solvent is being reused, it's in a proper condition. Another way of dealing it is truck it to external recycling party. So in that case, the highly concentrated streams are trucked off from site, and then the recycling party is basically making sure that it's going to be recycled and upgraded into such a quality that it can be reused in your facility or another facility. Or in some cases, external disposal is also an option in case there is no good way of separating the solvents or improve the quality to such extent that it can be reused. So these highly concentrated streams, there are, let's say, quite a number of options for that. The low concentration waste streams, coming from, for instance, cleaning and washing operations, and we take an arbitrary range of less than 5 volume percent. That is typically finds its exit in two ways, either by disposing it by a third party, or it's treated on site in a wastewater treatment plant. Well, disposing it to a third party is obviously an easy way of dealing with it, but it's in general fairly costly. And it can involve a lot of truck movements, and especially that has obviously some HSE consequences. So that is not always preferred. The alternative, treating it on site in a wastewater treatment plant, also can have some additional problems, and that brings me to my second question. For those of you who have experience with wastewater treatment plants on API manufacturing sites, I'm wondering whether you have had any problems with those wastewater treatment plants, or maybe if you are aware of it. So the replies can be none, because you're not involved in the operation or design of such a wastewater treatment plant. It can be none because you believe everything works fine. But there also can be some problems caused by, for instance, hydraulic limitation, that the capacity of the wastewater treatment plant is simply too small, maybe due to extension of the production site. It can be that the wastewater treatment plant is underperforming, and this can be due to toxic or non-biodegradable components. Or simply the wastewater treatment plant does not meet the requirements set by the authorities of the permits, simply because these requirements become more stringent. Okay, I see there are quite a number of people who are not involved in wastewater treatment plants and treating wastewater. So for you guys, there's let's say some opportunity to learn something about it during this talk. I also see that hydraulic limitation is often a problem apparently, simply because the capacity is too small. Okay, I will share again. Go to the next slide. Yeah. So what we have done with within the pharmaceutical industry is that we have been asking around, doing some interviews for us of customers, etc., to see what the issues are with wastewater treatment plant performances. And actually, quite a large number do have some issues with these wastewater treatment plants. And in most cases, this can be related to the presence of solvents. So in some cases, the solvent is simply toxic to the biomass, because these wastewater treatment plants often have a biotreater as a means to reduce the biological oxygen demand. It can be that that elevated levels of solvents exceed the BODSC removal capacity, and that the final effluent quality simply will not be met. In those cases where you have, let's say, a solvent that simply is not or hardly biodegradable, it will flush through the system as it is. And the high levels of solvents can cause limitation in the expansion of the production of the site due to constraints in the water treatment plant. So these are problems we quite often encounter in our review of various plants. When we are discussing with clients to see how we can solve it, then obviously one way of dealing with it is to isolate that troublesome waste stream which going into the plant and have a dedicated treatment for that. And by doing that, solve the issues with the wastewater treatment plant. And then if you look at the different technologies to treat solvents containing wastewater streams, then you're looking at technologies like steam stripping, distillation, and it can be fractional or extractive in cases of azeotrophs, add or adsorption, membranes like perforation. But we are focusing today on liquid-liquid extraction. But we have enabled that in a let's say different way than the traditional liquid-liquid extraction that is quite well known in the industry. So we do that by MPPE, and that is the abbreviation for Micro Porous Polymer Extraction. So the principle is as follows. What we have is very small particles, and you can see on the slide it's approximately 1 millimeter in length. It's a cylindrically shaped particle. And if you look at this particle with a scanning micron electroscope, then you will see that it is very porous. So you see the pores at the bottom right, and basically these are roughly a few microns large, those pores. So what we do next is that we have a solvent in these pores, and this solvent, this is basically your extraction liquid to remove the solvents from the wastewater. So this extraction liquid is in the particles present at roughly 70 volume%. So that means that if you have these particles in your hand, you're holding 70 volume% of liquid. What we then do is that we put these particles in a packed bed inside a vessel or a column, and then we bring the wastewater in contact with these particles, and basically what happens is that the solvents will migrate from the water phase into the extraction liquid. And they do that according to a fixed ratio. It's called the partition coefficient. So this is the basis of extraction, and this is also explaining how we have packed the extraction technology in a different way. One comment here, if you have very polar components, like ethanol was one of the solvents that was mentioned, then they have a very low partition coefficient, and then the extraction principle will not work. But we can use an adsorption type of media and operate it in the same way. So how do we get from this particle into an actual process that can work to treat the wastewaters coming from the API manufacturing? So we, like I said, we put these in a vessel, and then we have a feed water containing the solvents, and we have an upflow direction of the feed water through the column, through the vessel, and then basically the treated water comes out quite clean. You can imagine that this is a process which cannot last forever, so at some point we need to regenerate the column. And we do that by using low pressure steam. Low pressure steam for us means it's steam of approximately 112 degrees centigrade. When we do that, what happens is that the column is heated up, and the solvents that are in the extraction liquid are becoming volatile. We send it to a condenser, and in the condenser, basically, we condense both the steam and the solvent that was released by the media. Well, the solvent, we can skim it off in the separator, and the water below the solvent is recycled and is mixed with the fresh feed water again. So if you look at it as a black box, then you see the feed water coming in, treated water coming out, a little bit of steam coming in, and a pure solvent coming out. So how do we operate that in order to make this batch process continuously? Well, it's very easy. We have two columns. One is in extraction mode, one is in regeneration mode. And just to give you an idea, the steam consumption we apply in order to, let's say, regenerate the media is fairly low. It's 0.5% of the feed flow. That means for every cubic meter of water you're treating, you need 5 kilograms of steam. The removal efficiencies we typically obtain are in the range of 99+%, and we have some cases where 99.95% was reached and was also required. For a lot of applications, we will recover the hydrocarbons or the solvents as a pure component. And as you can see, we don't need any further chemicals, and neither we produce any waste sludge or off gas except the solvent. It's a fairly simple process. We have some small pumps in there. You don't see all the equipment here, but you can imagine, for instance, that the recycle stream needs to be pumped into the feed stream. But again, this is a very small stream because we only have a very low steam consumption. So we are using only a fraction of the feed will be used for steam. Again, the same note that in case of polar components, obviously in this separator vessel, you don't get the solvent as a separate stream, but you have to regard the whole stream, so the condensed steam, including the solvent, as a waste. Okay, this principle has been used a lot, and we are going to take a little side trip to a different industry, and that is the oil and gas industry. And the reason for that is very simple. This is the industry where we had our first references, and this is the industry we also provide us for, let's say, for most of our projects. But we do want to move into the pharmaceutical industry as well. And that's why we participate in events like this. But I want to share with you two references from the oil and gas industry, just to demonstrate that it's a proven technology and it's a reliable technology. So very quickly, this is a site in the Netherlands where we are treating gas-produced water. That is water coming up with the gas exploration, and it contains a lot of, as you can see, BTEX. So that is benzene, toluene, ethyl benzene, and xylenes. And these are quite toxic, so these cannot be discharged. So they are the stream needs to be treated. And if you're looking at the composition, then you're basically looking at very high concentrations of these components. And in this particular case, it had to be treated in such a way that it went from, let's say, average 2000 ppm down to 0.5 ppm. In this case, it's a small unit. It's only 6 cubic meters per hour. This unit has been in operation for almost 25 years. It unfortunately did not meet its jubileum at 25 years, but okay, still it's a long time. So it's a proven technology and it has been around for a long time. The second example I would like to share with you is that basically illustrates that it is also a very reliable technology. In this case, we also treating gas-produced water. However, the flow is much larger. So you're looking at 140 cubic meters per hour, but the removal efficiency is somewhat similar. The inlet is 2,500 ppm of BTEX mostly, and that has to be reduced to 30 ppm. On the top right picture, you see the module that was built for this, and it looks huge. It is huge, but it's also built according to oil and gas standards, so it's not applicable for the pharmaceutical industry. What I want to stress is that this unit is built on what we call a floating LNG plant, and it's one of the biggest projects in oil and gas history. And basically, this ship relies on our performance in order to, let's say, discharge the water overboard and as a license to operate. So a very expensive project is relying on the technology. Just illustrating its reliability. Well, what solvents we can remove with MPPE? Then obviously we have, let's say, the aromatic and the aliphatic compounds, like I already mentioned, the benzene, toluene, xylenes, but also a whole series of chlorinated components, which are obviously used a lot in API manufacturing as well. As indicated, the polar components are not really very well removed with the extraction technology, but we apply a different type of sorption media for that. And that is operated in the same way. So we also apply the steam regeneration. We have the particles inside the bed, and even the two different sorption and extraction media can be combined in a single vessel. So for the polar components, what we have done over the past years is some examples are IPA, so isopropyl alcohol, acetone, THF, DMF, and all these components are typically removed at more than 99% efficiency. The only two ones that cannot be removed with either of the two types of media, so the extraction media or the adsorption media, are methanol and ethanol. And that has to do with the fact that these are too much like water. So our experience in the oil and gas industry was noted by some colleagues of us in the Scandinavian business unit, and they thought of our technology when they were approached by a pharmaceutical company that was looking to solve a problem with a waste stream containing toluene. And the waste stream was coming from a fermentation process, and that contained 1000 ppm of toluene, which means it is oversaturated because typically the solubility is 500 ppm. And they wanted to have an outlet concentration of less than 1 ppm. Previously in the plant, they've been using steam stripping, but that was not preferred due to basically two reasons. One was the very high energy consumption. Again, in our case, we use only 1 kilogram of 0.5 kilogram of steam for a cubic meter water treated. But they also had a lot of issues with fouling of the stripper. So some components were attaching to the surface of the media transfer particles inside the stripper, and they basically reduce the efficiency of the stripper over time, and that need to be cleaned, which involved downtime of the stripper. There were significant HSE risks attached to that. The client had to, let's say, hire an external company for that, and that also created the waste stream. So when we presented the technology, the client was interested, but obviously in the end you need to provide a proof of principle. And for that, we are able to do lab tests in our facility. And in this case, the client witnessed those tests. So what we have done is we have used what we call a micro unit in order to test with the actual feed water that was delivered in an IBC container, and treating that by the extraction media. So in the picture here, you see the micro unit containing the columns with the media. These are the columns, and then it's a fully automated MPPE unit, but just very small. The analysis for toluene was done by a third-party lab, also to prove it in an independent way. And what we noticed that if you look at the samples and the results from the analysis we got back from the lab, then the toluene feed concentration appeared to be varying a lot, and that had to do with the fact that it's an oversaturated solution. So there's more toluene in there, and that is, yeah, physically you can describe it as small droplets toluene inside the water. The experiments were executed at ambient temperatures, and basically we had runs consisting of 13 cycles of loading and regeneration. So every column was loaded for 1 hour while the other was regenerated, and then it was switched. So the total test per run consisted of approximately 27 hours. Well, here are some results, and basically you can see that removal is quite efficient. So within a certain run, we executing 13 cycles, as I explained, and we are taking samples every now and then. In this case, after cycle number 2, 3, 4, 12, and 13. Obviously, we did more experiments, but these are the results I wanted to share. And if you look at the inlet concentration, then you see this variation I mentioned previously, due to the fact that the toluene is not only nicely dissolved in the water, but it also forms droplets. And you can also see that on the picture of the inlet sample, it's turbid, so you cannot easily look through it. And that is an indication that small droplets are present. Well, if you then look at the outlet, so coming out of the column with the extraction media, then you see that the concentration is decreased from, let's say, on an average, I think it's around 80,000 ppm down to ppb, sorry, down to now around 2 to 7, 8 ppb. So that removal efficiency is extremely high. We know that toluene is for us a relatively easy component to be removed, but it also is quite clear that the target concentration of 1 ppm is met, and actually quite easy. Yeah, like I said, if you look at the sample of the treated water, that is fully clear. So also the toluene that is present as small droplets are removed. And that is also our experience with the technology, that dispersed hydrocarbons or dispersed solvents in this case are removed as well. Okay. Then obviously after this testing, we needed it to convert this in an actual installation. So the requirements remain the same. So going from 1000 ppm toluene inlet to less than 1 ppm. The feed flow was 4.5 cubic meters per hour. And the client required this unit to be as a standalone unit, including its own control system, power supply, etc. And they wanted to have this close to the tank farm. And in the back of the picture, you see some tanks. So it also needed to be housed in some kind of structure, and therefore we decided to propose a containerized version. So basically the unit is built in 2 containers which are stacked on top of each other. In this particular case, the steam for regeneration was supplied by the client. These are the steam pipes. In some cases, the clients do not have steam on that point, or not sufficient steam, or not steam of the right pressure. In that case, we can also offer that as a part of the unit. Because this unit is in an zoned area, we had to comply with ATEX Zone 2 in order to make the installation explosion proof. So these are some pictures of the inside of the container. So basically we have, let's say, the 2 columns which are sticking through the, let's say, the bottom of the top container. You see some steam supply coming in, and it's maybe a bit difficult to see, but basically, like I said, these columns are sticking to the roof of the bottom container. And here you see a tank which is used to collect some water during the regeneration. But in the end, this water is also being treated as well. Another example from the industry is that we ran into a client that was not able to treat their wastewater according to the requirements that were set by the local authorities. In this case, the BOD, so the biological oxygen demand of the wastewater, should be less than 300 ppm in order to discharge it to the sea. And the client was not able to meet it. They had various technologies tested, but yeah, basically the biological treatment step was always in trouble due to the presence of very high concentrations of chloroform, dichloromethane, and aromatics. So what we proposed, we said, well, maybe there's a way of dealing with it by first removing these toxic components, so the chloroform and the dichloromethane, and then use, let's say, a very simple biorotors, or it's one of the ways of executing a biological treatment to treat the rest of the BOD. Well, in this simple graph, you can see that if you look at the BOD values, they go up to 3000 ppm. But the majority, or let's say a significant part of it, is caused by the chlorinated components, which is depicted with this red part of the BOD content, and that is basically removed in excess of 99%, and then after the biotreater, the rest of the BOD, so coming from roughly 1500 ppm down to 300 ppm, is done in, let's say, a traditional biological treatment. So these are 2 examples whereby MPPE was used to treat certain wastewaters. So then I come to the conclusions. MPPE can provide an alternative for treatment of water streams containing solvents. Again, it's an alternative. We are obviously, as Veolia, we can also propose other technologies, but this is certainly one for the more difficult streams. Despite the fact that you might not heard of it, it's a very proven and mature technology. and it has been applied on large scale for several decades now. If you compare it with some of the alternative technologies, in particular distillation and steam stripping, then the energy efficiency is much higher. And we did a comparison study for an application, not in the pharma, but in the petrochemical industry, where we showed that we could have up to 90% of energy savings when compared to steam stripping. So this has been for obviously for a lot of companies, both inside pharma, outside pharma, and hot topic in order to meet their sustainability goals. For new applications, we can test it fairly simple in the lab, and the lab results, our experience so far is that it can be fairly well translated into a full-scale installation, and as such, the testing itself is I would say a good way of scanning the technology for different applications. So we actually have been putting a lot of effort in testing different types of solvents, the removal of different types of solvents, and in practice it works quite well. So we are now looking to get additional references for full scales as well, like the one I just described in Scandinavia and France. This concludes my presentation. If there are questions, I'm obviously available to reply to those.
Thank you, Jeroen. So would anyone like to post their question in the chat, or please do unmute if you'd like to ask directly? We've got a nice small group here, so any queries, comments, suggestions, experience are all very welcome. Does anyone have a question? There's a golden opportunity for anyone. What do you think would be the biggest challenge facing like the manufacturers? Because I noticed that in this group, actually, most of the people attending are pharmaceutical manufacturers.
Mm-hmm. For us, the challenge is to first of all to get a better view on how typically wastewater treatment plants or wastewater streams in general are being handled. So we know that indeed some cases it's exported to a third party. In some cases it's treated on site. So to get a better view on that and what problems are arising, that is for us quite a challenge, because like I said, we are not very well known in the pharmaceutical industry. Our background is completely different. That's why we also did some interviews with various, I would say, large and reputable type of API producers. And what was striking is that when you talk to them very quickly and superficially, then in general there aren't too many problems or issues. But if you dig deeper and if you ask, for instance, what type of solvents do you use, then they say, well, this solvent, yeah, that we don't like to use solvent because it presents problem in the wastewater treatment plant, or it's too expensive to truck it off. Or so if you dig a bit deeper, then there are actually a lot of opportunities to improve the whole solvent handling, the waste handling, and to get a better view on that is a challenge for us. And then, yeah, like with a lot of industries, the pharmaceutical industry has its own ways of working, its own ideas. So to convince that with completely new technology that there are opportunities to improve, that yeah also takes some time. But in general, I would say for a lot of API manufacturers, they do also have a very, I would say, ambitious set of sustainability goals. And from that point of view, the technology fits in there quite well, especially looking at, for instance, the carbon footprint, which is lower compared to steam stripping or distillation. So I believe there are opportunities, but we just need to spread the word, basically.
Thank you. And related to that, what's the timeline in terms of deploying a study on site?
It can be quite quickly. So what we would normally do if a client has a certain problem, we would say, can you send us a sample? And then we do some testing, and we have different grades of testing. We can start with a very simple bench scale test to a full pilot study on site. Anything in between is possible. We obviously do it in phased in a phased project, because putting a containerized pilot unit on site is fairly expensive. It's complex. So first we try to get the proof of principle by doing these kind of bench scale tests, and then we slowly move on to other tests. Because it's, let's say, a physical chemical process, the test on site, for instance, doesn't need to take long. If you have a biological treatment, then some cases you have to wait a few months before the biological or biomass is adapted to the new chemical. So, but in our case, it's fairly straightforward, and I would say a test of 4 weeks, for instance, would be sufficient. And then it's up to the client what, let's say, kind of design validation they want, what type of procurement processes they have. But the units themselves, we would be able to supply them in between, let's say, 8 and 10 months nowadays. And the market is quite difficult to getting materials. But 8 to 10 months, so yeah, the whole process could be concluded within almost within a year. That's the type of timeline you have to think about.
Okay, thank you. Question: how does MPPE absorb or remove dissolved COD/BOD? Is there any special phenomena or properties that MPP has? And what is the lifetime for MPPE?
Okay, yeah, the lifetime is a good question. Let me start with that one. So the lifetime of the media is for us always depending on the quality of the feed water. We have clients which use MPPE as a kind of, yeah, I would almost say like a kind of waste disposal. So they put every stream they have in there. In that case, the media is completely fouled, and yeah, we have a lifetime of approximately maybe 6 months. But that is not the proper way how to operate. But for them, it's cheaper than trucking it off. If you look at the more clean applications, the lifetime of the media can run up to 4 up to even 7 years. So if you provide us with a stream which doesn't contain too much suspended solids, especially that can be damaging, then it's lifetime of several years is applicable. The first part of the question: how does MPP will remove sort of dissolved COD and BOD? Yeah, so basically it's the removal process itself. The physical process is either based on extraction or absorption. So the BOD or COD will simply absorb to the media, or will be extracted by the extraction liquid inside the media. So depending on the type of component you want to remove, we will select the type of media, and then it's being removed. And that means that like I explained, it cannot continue forever. So at some point you need to regenerate the media, and that regeneration we do it with steam, and by I would say for the components we normally treat, that regeneration is 100%. So in the next cycle, it will perform just as good as in the first cycle. The only thing what we see but that is a very gradual process, is that we see some fouling of media occur over the lifetime of the media, and therefore at some point you need to replace the media. So the recovery in principle is 100% after regeneration, but because of fouling, some components will attach to the media and will not let loose. Because of that process, we have to replace it every now and then.
Thank you. Does anyone else have a question? Or any comments or suggestions? Otherwise, we will let Jeroen leave. But oh, I just got a question from Dwayne. If the waste stream were to increase as a result of an increase in production due to reasons like the expansion of existing production capacities in the plant, etc., how easy would it be to scale up the existing MPPE system to handle the increased amount? Would that entail the construction of a new skid?
Good question, because from our oil and gas experience, we know that the flows typically are varying from very low 10% to 100%. There are two ways of dealing with it. If this expansion of the plant and so the future increase of the wastewater flow is foreseen, then we typically would recommend to install, let's say, a larger unit from the start. And because let's say the turn down ratio of this technology is extremely low, so you can go down to 5 or 10% of the feed flow, and it still will operate as required. In case another solution would be just to have the large size columns, but to do not completely fill it up with media, but that is not so efficient. In case the future expansion is not foreseen, yeah, then unfortunately you cannot escape from it then other than adding another system.
Thank you. Dwayne, does that answer your question? Great, thank you. Does anyone else have anything to ask Jeroen? Okay, is there any special process for solvent extraction after steam regeneration, or isn't conventional API floating tank?
If I understand the question correctly, the person is asking how to remove the solvent after the steam regeneration. So when we regenerate the media with steam, then we send the steam together with the solvents that have been regenerated. We send that to a condenser, and if the component that is removed, so the solvent that is removed, is not miscible with water, then in the separator you get let's say a floating layer of solvents. In case of toluene, you will find a layer of toluene on top of your water. In case of, for instance, chlorinated hydrocarbons, which are mostly heavier than water, you will find a layer below the water phase. So that can be skimmed off, and therefore you get your solvent as a pure product out of the system. Now, if you look at components like isopropyl alcohol or acetone, these are fully miscible with water. So you don't get in your separator, you don't get a separation of an organic layer. So in that case, yeah, we regard what comes out of the regeneration process as a waste. However, if you recall let me illustrate it by a different example from a different industry. We're currently building a unit treating IPA waste, so isopropyl alcohol waste, containing approximately 1500 ppm the wastewater, which is way too high to be discharged. And we treat that with the same system, and the regeneration stream has approximately 30 weight% of IPA. And that means that going from a very large stream containing 1500 ppm, you go basically roughly a factor 200 smaller stream and much more concentrated. And in this case, although it's still a mixture between water and IPA, because the concentration of the IPA is very high, it can be reused by further distillation. So depending on first the type of component, is it miscible or not, you get a clean stream, or you get a very concentrated stream that in some cases can be further upgraded by a distillation or system, for instance. Does that answer your question?
I think so. Thank you, Jeroen. Does anyone else have a final question? You can unmute if you feel you'd rather not type. Otherwise, I'd like to thank you very much for your time, for attending, but also Jeroen for sharing your expertise with us this afternoon. And we really very much appreciate the presentation that you've made. And I think that's been of interest to everybody. We look forward to potentially seeing you again soon. And in the meantime, we want to thank you and hope you'll have your, I think it's lunchtime now, isn't it, for you? So
yes, I will definitely have my lunch now.
So in the meantime, to everyone, stay healthy, stay fit. We wish everyone a good rest of day or evening. Oh, Dwayne has one last question. For the media that has been fouled and cannot be regenerated, what are the disposal options available, e.g. landfill, incineration, etc.? Is there a possibility of recovery off-site?
Basically, well, this is a technical session, but just a bit of business then, because I need to explain in this case the business model we have. Basically, the client is buying an installation, but we keep ownership of the media. So if the media is beyond regeneration, it needs to be replaced. We take it back and we replace it with new media. What we do with the spent media depends again on what the state is. If the state is sufficiently good, we have what we call a rejuvenation process. So we do that in our own facilities where we also produce the media. And in some cases, it's beyond repair, I would say. And in that case, we simply dispose of it in well, obviously way which is in line with legislation, etc., and good and healthy practices. But I would say 90% of the media, spent media we get back in our facility is being reused.
Brilliant. Thank you very much. That was a last minute question there from Ali. Also, thanks to Dwayne for your questions. And again, for everyone for joining us this afternoon. So wish you all well. And until we see each other again, take care, everybody. Thank you.
Okay. Thank you. Bye-bye.
Bye-bye.